Hello everyone, hope you are all doing well. In this video, I will be discussing Chapter 3 of Class 12 Chemistry, Chemical Kinetics. Without wasting any time, let's directly start with the subject. Chemistry is concerned with change. Substances with well-defined properties are converted into other substances with different properties by chemical reactions. For any chemical reaction, we speak about three aspects. The first is feasibility of chemical reaction. Feasibility tells us whether a chemical reaction is possible or not. So this can be predicted by thermodynamics, right? Yes. So when is a chemical reaction feasible? How do we come to know that whether a chemical reaction is possible or not? We have studied that chemical reaction with change in Gibbs free energy less than 0, that's a reaction with delta G which is less than 0 at constant temperature and pressure is feasible. The second aspect is to find out the extent to which a reaction will proceed. All reactants are converted into products. Can we get back reactants from the products? So this can be determined from chemical equilibrium. The third aspect is to find out the speed of a reaction. That is, time taken by a reaction to reach the equilibrium. So these three aspects are what we are trying to study with respect to a chemical reaction. For understanding a chemical reaction completely along with its feasibility and extent to which that chemical reaction occurs, it's equally important for us to know rate of the reaction and the factors which controls rate of these chemical reactions. It is this branch of chemistry which deals with study of reaction rates and mechanism of chemical reactions is called as chemical kinetics. The word kinetics is derived from Greek word kinesis, which meaning is movement. Thermodynamics tells us only about the feasibility of a reaction. Means the thermodynamics tells us only whether a reaction is possible or not. Whereas chemical kinetics tells us the rate of reaction. That is, how fast or how slow a particular reaction is. Also, chemical kinetics describes the conditions by which reaction rates can be altered. For example, thermodynamic data tells us that diamond shall convert into graphite. This conversion of diamond to graphite is very slow process. It takes thousands of years for a diamond to get converted into graphite. Conversion rate is so slow that one person in his entire lifetime will not see a diamond becoming graphite. Therefore, most of us think that diamond is forever and it will remain as diamond. Consider ice cubes which are placed outside. What will happen to these ice cubes? Every ice cube will melt to form water. This reaction is fast. Similarly, if you add a spoon of salt into water taken in a glass, salt dissolves very quickly. Consider rusting of iron articles which is placed outside. So that is exposed to air, water and moisture. It takes weeks together to form rust. So rusting is considered as a slow process. When we study a chemical reaction at the macroscopic level, we speak in terms of amount of reactants reacted or product formed and rates of consumption of reactants or rate of formation of products. But at the microscopic level, that is at the molecular level, we need to study the reaction mechanisms involving orientation and energy of molecules which are undergoing collisions. Now, let us take an example to understand what this macroscopic and microscopic level is. Imagine you are flying in an aeroplane. You see so many trees, buildings, roads, vehicles, parks, etc. on the ground. If you look at those buildings from aeroplane, can you think of what might be happening inside the building? How many rooms are present in the building? What are all the things present inside the building? Who are all present inside? Not possible, right? But instead, if you look to the building more closely, if you enter into the building, you will get a clear picture of what are the things happening inside. Right? When we glance from the top, we get a macroscopic view, and as we enter inside, we get a clear picture of what is happening. So that is microscopic view. Similarly, to understand a reaction, we need to study at molecular level, that is in terms of energy of molecules and how the molecules are oriented. For example, consider the reaction between hydrogen and oxygen to form water molecule. At macroscopic level, we speak about this reaction as 1 mole of hydrogen is reacting with 1 mole of oxygen to form 1 mole of water. At microscopic level, we need to study whether the molecules are colliding with one another during the reaction or not. What is the energy of molecules involved in this particular reaction? Let us first learn about the reaction rate to understand other concepts related to chemical reaction. By mixing of aqueous solutions of silver nitrate and sodium chloride, we get the precipitate of silver chloride, which occurs instantaneously. So this is a fast reaction. Iron nail exposed to air and moisture, it takes a few weeks or months to rust. Rusting of iron is a slow process. Reactions like inversion of cane sugar and hydrolysis of starch, which proceed with a moderate speed. When we have a car or bike, its speed is expressed in terms of change in position with time, or by knowing the distance covered with respect to time. Similarly, speed of a reaction is defined as change in concentration of a reactant or product in unit time. It is expressed in the terms of rate of decrease in concentration of any one of the reactants, or it is expressed in terms of rate of increase in concentration of any one of the products. Let us consider a reaction where from 1 mole of reactant R, we get 1 mole of product P. So the reaction is R giving P. Let us consider R1 and P1 as concentration of reactant R and product P at a time T1. So here these square brackets are used to represent the concentration. Similarly, let us consider R2 and P2 as concentration of R and P at a time T2. So the time interval can be written as delta T is equal to T2 minus T1. Change in concentration of the reactant can be written as delta R is equal to R2 minus R1. Similarly, change in concentration of product P is written as P2 minus P1. In all this equation, remember that the square brackets are used to express molar concentration of reactants as well as products. Rate of disappearance of R is given by decrease in concentration of R divided by time taken, which is equal to minus delta R divided by delta T. Similarly, rate of appearance of product is given by increase in concentration of P divided by time taken. This is equal to plus delta P divided by delta T. As concentration of reactants is decreasing, delta R is a negative quantity. So it is multiplied with minus 1 to make rate of the reaction as a positive quantity. So we have the expression minus delta R divided by R. These two equations represents average rate of the reaction. It is denoted by RAV. Concentration of reactants and products when plotted as a function of time we obtain the graphs as shown here in the figure. During a chemical reaction, reactants are consumed. The concentration of reactants decreases. So, we see a decreasing curve for reactants. And the products are getting formed, so the concentration of product increases. Hence, an increasing curve for products. If we want to predict rate of a reaction at a particular instant of time, then average rate cannot be used because average rate is a constant for the time interval for which it is calculated. So, to express rate of a particular moment of time, we determine the instantaneous rate. Mathematically, for an infinitesimally small dt, instantaneous rate is given by R instantaneous is equal to minus dr divided by dt, which is equal to minus dp divided by dt. To determine the instantaneous rate graphically, draw a tangent at time t on either of the curves for concentration of R and P versus time and calculate its slope. The value of slope will give us the instantaneous rate of the reaction. Now, let us consider a few chemical reactions and see how we can write rate of the reaction for these chemical reactions. First one, Hg liquid plus Cl2 gas giving HgCl2 solid. Here in this equation you see that 1 mole of mercury is reacting with 1 mole of chlorine to form HgCl2. The stoichiometric coefficients of reactants and products are same. Therefore, I can write rate of reaction is equal to minus delta Hg divided by delta T, which is equal to minus delta Cl2 divided by delta T, which is equal to plus delta HgCl2 divided by delta T. Rate of disappearance of any of the reactants is same as that of rate of appearance of the products. Example 2. 2Hi gas giving H2 gas plus I2 gas. Here in this reaction, 2 moles of Hi decompose to produce 1 mole each of hydrogen and iodine. Here, if you observe the reaction, stoichiometric coefficients of reactants or products are not equal to 1. When we write rate of such reaction, where stoichiometric coefficients of reactants or products are not equal to 1, rate of disappearance of any of the reactant or the rate of appearance of products should be divided by their respective stoichiometric coefficients. So for this reaction, rate of reaction is equal to minus 1 by 2 delta Hi divided by delta T. So we have divided it by 2 because the stoichiometric coefficient for Hi is 2. Similarly, the rate of reaction is equal to delta H2 divided by delta T, which is equal to plus delta I2 divided by delta T. Example 3. 5Br minus aqueous plus BrO3 minus aqueous plus 6H plus aqueous giving 3Br2 aqueous plus 3H2O liquid. For this reaction, rate of reaction can be written as minus 1 by 5 delta Br minus divided by delta T. That's equal to minus delta BrO3 minus divided by delta T, which is equal to minus 1 by 6 delta H plus divided by delta T, that is equal to 1 by 3 delta Br2 divided by delta T equals to 1 by 3 delta H2O divided by delta T. If we have a gaseous reaction at constant temperature, then its concentration is directly proportional to partial pressure of a species, and therefore rate is expressed in terms of rate of change in partial pressure of the reactant or the product. For example, if I consider the reaction of 2Hi in gaseous state decomposing to give hydrogen gas and iodine gas. If I need to write the expression for reaction rate for this particular reaction in terms of partial pressure of the reactant and product, then I can write rate is equal to minus dphi divided by dt. That is, decrease in the partial pressure of the reactant Hi divided by the time interval dt. So this is also equal to dpH2 divided by dt, which is equal to dpi2 divided by dt. Rate of a chemical reaction depends upon the experimental conditions such as concentration of the reactants. If I speak it in terms of gases, then it should be pressure instead of concentration. Also, the rate is affected by temperature, catalyst. Now, let us study how these factors affect rate of a reaction one by one. The rate of a chemical reaction at a given temperature depends on the concentration of one or more reactants and products. The representation of rates of reaction in terms of concentration of the reactants is known as rate law. It's also called as rate equation or rate expression. Now, we know that whenever a chemical reaction is occurring, the concentration of reactants decreases as the time passes. As a result, the rate of reaction decreases. In general, we can tell that rate of a reaction increases with increase in concentration of reactant. If we have more reactant, more will be the reaction that is taking place. So, concentration of the reactant is directly related to rate of a chemical reaction. So, we can tell that rate of reaction depends upon concentration of reactants. Now, if we consider a general reaction where A moles of A is reacting with B moles of B to give C moles of C and D moles of D, where these A, B, C, D are the stoichiometric coefficient of reactants as well as product. Now, rate expression for this reaction is written as rate is directly proportional to concentration of A raised to X multiplied by concentration of B raised to Y. These exponents X and Y may or may not be equal to the stoichiometric coefficients A and B of the reactants. We cannot write the values of the X and Y just by looking into chemical equations. It has to be determined experimentally. If we remove the proportionality symbol in the expression by introducing a constant, then the expression for rate can be written as rate is equal to K into concentration of A raised to X into concentration of B raised to Y, where K is a proportionality constant and we call it as rate constant. So this particular equation which relates rate of a reaction to the concentration of reactants is called as rate law or rate expression. Thus we can tell rate law is the expression in which reaction rate is given in terms of molar concentration of reactants with each term raised to some power, which may or may not be same as that of stoichiometric coefficient of the reacting species in a balanced chemical equation. The same rate law can be written as minus dr divided by dt, which is equal to K into concentration of A raised to X into concentration of B raised to Y. Now this equation is known as differential rate equation. Now let us consider a few examples and let us see how we can write the differential rate equation as well as rate law for them. Example 1, 2NO plus O2 giving 2NO2. The rate equation for this reaction is rate equals K into concentration of NO raised to 2 into concentration of O2. The differential equation for this rate expression is written as minus dr by dt, which is equal to K concentration of NO raised to 2 into concentration of oxygen. For this reaction, the exponents of the concentration terms are same as that of their stoichiometric coefficients in the balanced chemical equation. This will not happen with all reactions. For example, let us consider the reaction between CHCl3 and Cl2 to give products CCl4 and HCl. The experimental rate expression for this equation is K into concentration of CHCl3 into concentration of Cl2 raised to half. Here, if you check clearly, you will see that the powers of the concentration terms in the rate law is not same as that of the stoichiometric coefficient of the reactants. Example 3, CH3COOC2H5 plus H2O giving CH3COOH plus C2H5OH. The experimental rate expression here is rate is equal to K into concentration of CH3COOC2H5 raised to 1 into concentration of water raised to 0. In these reactions, you see that the exponents of the concentration terms are not same as their stoichiometric coefficients. Rate law for any reaction cannot be predicted theoretically just by looking at the balanced chemical equation, but the rate law must always be determined experimentally. Now let us consider a few numericals and see how we can calculate rate of a chemical reaction. First question, for a reaction 2HI giving H2 and I2, if the initial concentration of HI was 0.80 mole per liter and concentration after 20 minutes was 0.68 mole per liter, calculate the rate of the reaction. Now, let us again go to the question and list what is the data that is provided to us through this particular question. So they told us that the initial concentration of HI was 0.80 mole per liter. So initial concentration means during the starting of reaction. So the reactant we have taken is 0.80 mole per liter. So I can consider that time as 0 minutes. So I'll write T1 is 0 minute. So the concentration of HI was 0.80 mole per liter. So I'll denote concentration of hydrogen iodide at time T1 is HI1, that is equal to 0.80 mole per liter. So they told that concentration after 20 minutes was 0.68 mole per liter. Now the time is 20 minutes later. So I can consider this time as T2 and the concentration of hydrogen iodide, I'll denote it as 2, that is equal to 0.68 mole per liter. We are asked to calculate rate of the reaction. So we need to calculate what is rate of this particular reaction. Also in the question they have given us the chemical equation 2HI giving H2 and I2. For this particular reaction, we will write the expression for rate. So rate is the decrease in the concentration of reactant, or it is how much product that is formed. So I can write here the reactant is HI. So it is minus delta, that is change in concentration of reactant to the time interval. So since we have stoichiometric coefficient 2, we have to divide it. So it's minus 1 by 2. So in terms of formation of product, the rate is written as delta concentration of hydrogen divided by delta T. And this is also equal to the rate of formation of iodine. So it is delta I2 divided by delta T. So from the question, we are provided with concentration of the reactant hydrogen iodide and we are asked to calculate rate of the reaction. So I will use the expression rate is equal to minus 1 by 2 change in concentration of hydrogen iodide to the change in time. So the formula that we will be considering is rate is equal to minus 1 by 2 change in concentration of hydrogen iodide divided by delta T. So this can also be written as minus 1 by 2. The change in concentration of hydrogen iodide is Hi2 minus Hi1, and delta T is T2 minus T1. Now let us substitute into this formula. So it's minus 1 by 2, and concentration of Hi at 20 minutes is 0.68 mole per liter, minus at T1, that is 0 minutes, concentration is 0.80 mole per liter, divided by T2, it's 20 minutes, minus T1, that is 0 minutes. So the unit is mole per liter in the numerator and it is minutes in the denominator. Simplifying this, I can write minus 1 by 2, 0.68 minus 0.80 is minus 0.12, divided by 20 minus 0 is 20. So minus into minus, that would become plus 0.12 divided by 2 into 20, that's 40. And after simplifying this, 0.12 divided by 40, we will be getting the answer as 0.003. Now we need to write the unit. So here you can see in the numerator we have mole per liter. In the denominator we have minute. Taking this upwards, I can write the unit is mole per liter per minute. And this is the answer. Next question is, ammonia and oxygen react at high temperature according to the equation. So they have given us the equation 4NH3 gaseous state plus 5O2 gaseous state, giving 4NO in the gaseous state plus 6H2O in the gaseous state. In an experiment, the rate of formation of NO was found to be 3.2 into 10 to the power minus 3 mole per liter per second. Calculate the rate of formation of H2O. So in the question, they have given us the reaction between ammonia and oxygen, which is taking place at high temperature. So they also gave us the rate of formation of NO. So I can write the rate of formation of NO. So since that is the product, I can write delta concentration of NO divided by delta T. So this is the rate of formation of NO, and that is equal to 3.2 into 10 to the power minus 3 mole per liter per second. By giving this value, they have asked us to calculate the rate of formation of H2O. So since H2O is also a product in this particular reaction, we need to calculate delta concentration of H2O divided by delta T. So this gives us rate of formation of water. We need to calculate this. So we are provided with the equation for the reaction between ammonia and oxygen. That's we have 4NH3 plus 5O2 giving 4NO plus 6H2. So now according to this equation, I can write rate of this particular reaction is given by, it is the rate of decomposition of reactant, or it is the formation of product that gives us rate of a chemical reaction. So from this I can write it is minus, because decrease in the concentration of reactant, so it is delta concentration of NH3 divided by delta T. Since we have the stoichiometric coefficient 4, I have to divide this by 4. So we have rate that is equal to minus 1 by 4 delta concentration of NH3 divided by delta T. Similarly, oxygen is also reactant. So I should write minus, then the stoichiometric coefficient in the denominator I should write, then change in concentration of oxygen with respect to the time interval. And this rate is also equal to the increase in concentration of products. So here with respect to NO, I can write rate as 1 by 4 change in concentration of NO divided by the time interval delta T. This is also equal to the formation of water, that's 1 by 6 change in concentration of water divided by the time interval. So rate of this particular chemical reaction can be found out in terms of concentration of ammonia, or in terms of concentration of oxygen, or it can be found out in terms of concentration of NO. It can also be found out in terms of concentrations of H2O. So in the question, they have given us the rate of formation of NO. So means here they have given us delta NO divided by delta T, and they have asked us to calculate the rate of formation of water. So now let us consider this particular part of the expression for rate of the chemical reaction, and we shall find the answer that is required for us. So writing that particular part of equation that's required for us, we can write 1 by 4 change in concentration of NO divided by time interval, and that's equal to 1 by 6 change in concentration of water with respect to time interval delta T. Now we shall rearrange this. We need to find the rate for formation of H2O. So this particular part of the equation, I'll retain it and I'll take this 6 to the other side. So I can write the rate of formation of water delta concentration of H2O divided by time interval delta T, that's equal to 6 divided by 4 delta NO by delta T. So here delta NO divided by delta T is the rate of formation of NO. That's given to us in the question, and that is equal to 3.2 into 10 to the power minus 3. The unit is mole per liter per second. After simplifying this, (1.6) into 3, that comes out to be 4.8 into 10 to the power minus 3, and the unit is mole per liter per second. So the rate of formation of H2O is 4.8 into 10 to the power minus 3 mole per liter per second. In the rate equation, sum of these exponents, that is x plus y, gives the overall order of the reaction, where x represents order of reaction with respect to reactant A and y represents order of reaction with respect to reactant B. So therefore, from the rate law, which is telling us rate is equal to k a to the power x b to the power y, order of the reaction n is equal to x plus y. So order of a chemical reaction is defined as the sum of powers of concentration of the reactants in the experimentally determined rate law expression. Now let us see what is a zero order reaction, a first order reaction and a second order reaction. So in general, for a chemical reaction A plus B giving products, we write rate law, that is rate is equal to K into concentration of A to the power X, concentration of B raised to Y. So here we have order of this reaction is equal to x plus y. Now, for a given reaction, if x is equal to 0 and y is equal to 0, rate is equal to rate constant into concentration of a to the power 0, concentration of b to the power 0. So here now if I check the order of the reaction, so order is equal to x plus y. So now it is 0 plus 0, which is equal to 0. So when order of reaction is 0, we call it as zero order reaction. So when x is 0 and y is 0, that particular chemical reaction is zero order reaction. A reaction which is independent of the concentration of reactants. So here now rate law will be rate is equal to rate constant. So this is a zero order reaction. So a zero order reaction is independent of the concentrations of reactants. Now, if x is equal to 1 and y is equal to 0, or if we have x is equal to 0 and y is equal to 1. In this case, rate expression is rate is equal to K into concentration of A raised to 1, concentration of B raised to 0, or in the other case, its rate is equal to K into concentration of A raised to 0, B raised to 1. Now here order is equal to 1 plus 0, which is equal to 1. In the other way, its order is equal to 0 plus 1, which is equal to 1. So when order of reaction is equal to 1, we call it as first order reaction. So this is a first order reaction. So when we have two reactants A and B, order of the reaction depends on the first power of concentration of any one of the reactants. So now here rate is equal to K into concentration of A raised to 1, or it is rate is equal to K into concentration of B raised to 1. So clearly you see that order of the reaction is 1. Rate is directly proportional to the first power of the concentrations. If we have x is equal to 1 and y is equal to 1, or if we have x is equal to 0 and y is equal to 2, or x is equal to 2 and y is equal to 0. Let us write the rate law here. So rate is equal to K, concentration of A raised to 1, concentration of B raised to 1. Second case, rate is equal to K into concentration of A raised to 0, concentration of B raised to 2. And in the third case, we have rate is equal to K into concentration of A raised to 2 into concentration of B raised to 0. So in the first case, now if we check the order for this case, it is 1 plus 1, which is equal to 2. Case 2, order is 0 plus 2, which is equal to 2. Third case, order is 2 plus 0, that's equal to 2. So you see that order now is 2. Therefore, this is called a second order reaction. Here you see that rate of the reaction is directly proportional to second power of the concentration. So that is rate is directly proportional to concentration of reactant raised to 2 in simple terms. Let us see how we can solve any numericals related to the order of a chemical reaction. First question, for a reaction A plus B giving products, the rate law is given by rate is equal to K into concentration of A raised to 3 by 2 into concentration of B. What is the order of the reaction? In general, for a reaction A plus B giving product, we can write rate law as rate is equal to rate constant K into concentration of A raised to X into concentration of B raised to Y. So for this general reaction, order of reaction is given by the sum of the powers of the concentrations in the experimentally determined rate equation. So here for this general equation, order of the reaction is given by X plus Y. So for the given reaction, they have given us rate is equal to K into concentration of A to the power 3 by 2 into concentration of B to the power 1. So from these two equations, so if I consider general equation as 1 and the rate law for the particular equation as 2, by comparing them, I can write X is equal to 3 by 2 and Y is equal to 1. So therefore, we have order of the reaction that is equal to X plus Y, that is equal to 3 by 2 plus 1, which is equal to 5 by 2 or 2.5. So therefore, order of the reaction is 5 by 2 or 2.5. Second question, a reaction is second order with respect to a reactant. How is the rate of reaction affected if the concentration of the reactant is doubled? Second, the concentration of reactant is reduced to half. So in the question, they have told us it is a second order reaction. So we have, in general, any second order reaction, reactant A giving product, its rate is written as rate is equal to rate constant into concentration of A raised to 2. This is how we write rate for a second order reaction. Now let us consider first case, that is when rate is doubled. We'll see what will happen to rate of the reaction when concentration is doubled. So the initial concentration of the reactant was A. Now if the concentration is doubled, means that will become 2A. For example, if the initial reactant concentration was 5 moles per liter, now when it is doubled, that would become 5 into 2, that is 10 moles per liter. So that is the case. So I shall denote new rate as rate dash, R prime, R dash means rate prime, I'll denote it, and that is equal to K into concentration of A. Now it has become 2A and its square. So this 2 squared becomes 4. So I can write this as 4K into concentration of A. So this K into concentration of A is nothing but the original rate when the concentration of A is A. So I can write this as 4 into initial rate. So from this I can tell that when concentration of the reactant is doubled, rate of the reaction is increased by 4 times. So for a second order reaction, when you double the concentration of the reactant, rate of the reaction will be increased by 4 times. Now the second case, when concentration is reduced to half, it means that concentration of A will now be A by 2. The initial concentration is 5 moles per liter. Now for this particular case, the concentration would be 2.5 mole per liter. So I'll denote the new rate as R prime. So that is equal to rate constant K into concentration of A squared. So it is A by 2 squared. So this is equal to K into concentration of A squared divided by 4. So you can write this R dash, now it is equal to 1 by 4 K into concentration of A squared. And this K into concentration of A squared is nothing but the rate that we have represented here. So I can write R dash is equal to 1 by 4 into rate. So from this clearly we can tell that when concentration of the reactant is reduced to half, rate of reaction becomes 1 by 4th of the initial rate. So this is how you can find how the concentration of the reactant affect a second order reaction when concentration is doubled or the concentration is reduced to half. So when the concentration is doubled, rate of the reaction is increased by 4 times. When the concentration is reduced to half, rate of the reaction becomes 1/4 of the initial rate in case of a second order reaction. For a general reaction, AA plus BB giving CC plus DD. The experimental rate equation is written as rate is equal to K into concentration of A raised to X into concentration of B raised to Y. Here, order of the reaction is N is equal to X plus Y. From the rate law, we can write the expression for rate constant K is equal to rate divided by concentration of A raised to X into concentration of B raised to Y. Therefore, to write unit of K, I can write in the numerator it is concentration divided by time, and in the denominator we have concentration raised to N. We should note that the SI unit of concentration here is mole per liter and the SI unit of time is second. Now let us write the unit of rate constant for different reactions which are having different orders. We shall find the unit of rate constant. Rate law is written as rate is equal to K into concentration of A to the power X into concentration of B raised to Y. From this rate law, I can write rate constant K is equal to rate divided by concentration of A raised to X and concentration of B raised to Y. So here rate is change in concentration of reactant or product with respect to time, and in the denominator we have concentration of the reactants X and Y. So I can write this as concentration to the power N, where N is order of the reaction. So the SI unit of concentration we know that is molar, that is mole per liter. The SI unit of time is second. Substituting these SI units in the expression of rate constant, we can write the unit of rate constant as concentration is mole per liter divided by time, that is second, and this is divided by unit of concentration, that is mole per liter, its power N. Using the laws of exponent, I can write this as mole per liter per second, and in the denominator we have mole per liter to the power N, that can be written as mole per liter to the power minus N. Further simplifying using the laws of exponents, I can write this is mole to the power 1 minus N, liter to the power minus 1, minus of minus N is plus N, so it is N minus 1 per second. So this is the unit of K in general. Now let us find the unit of K for a zero order reaction and for a first order reaction. We know that for a zero order reaction, rate is equal to rate constant. This is because zero order reaction is the rate is independent of the concentration of reactants. So unit of K is equal to unit of rate. So we know that rate is change in concentration of reactant divided by time, and the SI unit of concentration is mole per liter. SI unit of time is second, and therefore unit of K for a zero order reaction is mole per liter per second. So this is the unit of K for zero order reaction. Now let us try to write the unit of K for a first order reaction. We know that for a first order reaction, rate is directly proportional to first power of the concentration of reactant. So I can write rate is equal to K into concentration of R raised to 1. K is equal to rate divided by concentration of R to the power 1. Rate is concentration divided by time, and in the denominator we have concentration to the power 1. SI unit of concentration is mole per liter divided by unit of time is second divided by concentration to the power 1, that is mole per liter. So mole per liter in the numerator and mole per liter in the denominator both gets cancelled with one another, and we have is 1 by S, which is nothing but second inverse when second is taken to numerator, and therefore the SI unit of rate constant for a first order reaction is per second. A balanced chemical equation never gives us a true picture of how a reaction is taking place. Means by observing the balanced chemical equation, we cannot tell whether a reaction is completed in one step or it is taking more than one step to complete the reaction. Molecularity helps in understanding the mechanism of the reaction, the number of reacting species. It can be atoms, ions or molecule that is taking part in an elementary reaction. It must collide simultaneously in order to bring about a chemical reaction. So these reacting molecules which bring about the collision are termed as molecularity of the reaction. The reaction is unimolecular when one reacting species is involved. For example, consider the decomposition of ammonium nitrate. Only one molecule is involved in the reaction. So, it is a unimolecular reaction. Consider the dissociation of hydrogen iodide. This reaction involves simultaneous collision between two hydrogen iodide species. So, this reaction is a bimolecular reaction. Trimolecular or termolecular reactions involve simultaneous collision between three reacting species. As an example, we can consider the reaction between nitrogen monoxide and oxygen to form nitrogen dioxide. The possibility of collision of three molecules and react simultaneously is very small. So, reactions with molecularity 3 are very rare and these reactions are very slow to proceed. So, we can conclude that the complex reactions involving more than 3 molecules in the stoichiometric equation must take place in more than one step. For example, KClO3 plus 6FeSO4 plus 3H2SO4 giving the products KCl plus 3Fe2SO4 plus 3H2O. This reaction which you can see here seems to be of 10th order. This is actually a second order reaction. This shows that this reaction takes place in several steps. The question is, which step controls rate of the overall reaction? The question can be answered if we go through mechanism of this particular reaction. For example, consider a relay competition. How can we tell a team possibly win the relay race? It depends on the slowest person in the team, right? If the slowest person could run a little faster, they may possibly win the race. So, the chances to win the relay race competition by a team, it depends upon the slowest person present in the team. Similarly, the overall rate of a chemical reaction is controlled by slowest step in the reaction. This slowest step is called as rate determining step. Consider the decomposition of hydrogen peroxide, which is catalyzed by iodide ion in alkaline medium. The reaction is 2H2O2 plus iodine. In the alkaline medium, we get 2H2O plus O2. The rate equation for this reaction was found to be rate is equal to minus D concentration of H2O2 divided by dt, that's equal to K into concentration of H2O2 into concentration of I minus. From this rate equation, we can tell that this reaction is first order with respect to both H2O2 and I minus. This is a second order reaction. From evidences, it is told that this reaction is taking place in two steps. In first step, H2O2 reacts with I minus to form H2O and IO minus. In the second step, H2O2 reacts with IO minus to form H2O and I minus and oxygen. Both the steps are bimolecular elementary reactions. The species IO minus, which is formed during the course of reaction, but actually it's not present in the overall balanced equation. So the species IO minus is called as an intermediate. Among the two steps that is involved in this particular reaction, first step is the slowest step, and therefore step 1 is rate determining step. Thus, the rate of formation of the intermediate IO minus will determine rate of this particular reaction. After understanding what is order of the reaction and what is molecularity for a reaction, now let us look into the differences between order and molecularity of a reaction. Order of a reaction is an experimental quantity. It can be 0, even a fraction, but molecularity cannot be 0 or a non-integer. Order of a reaction is applicable to elementary as well as complex reaction, whereas molecularity, it's applicable only for elementary reactions. For complex reaction, molecularity has no meaning as such. For complex reaction, order is given by the slowest step, and molecularity of the slowest step is same as that of order of the overall reaction. Just now we have studied the concentration dependence of rate. That's what we have termed as differential rate equation. Now, in all cases, it's not convenient to determine instantaneous rate. It is difficult to determine rate law, and hence it's difficult to determine order of the reaction. So, in order to avoid this difficulty, we will integrate the differential rate equation to obtain a direct relation between concentrations at different times and rate constant. The differential rate equation after integration is called as integrated rate equation. The integrated rate equations are different for the reactions of different reaction orders. Now we shall determine the integrated rate equations for zero order, first order chemical reactions. Let us write the integrated rate law for a zero order reaction. So let us consider a zero order reaction are giving products. Since the reaction that we have considered is zero order, I can write the differential rate law as minus dr divided by dt is equal to K into concentration of R naught raised to 0. So this is equal to K into 1. So therefore I can write the differential rate law is minus dr divided by dt is equal to K. Rearranging this equation, I can write minus dr is equal to K into dt. Changing this minus side towards the right hand side, I can write dr is equal to minus K into dt. Integrating on both sides, I can write integration of dr is equal to minus K is a constant, integration of dt. Integration of dr gives us r, which is equal to minus K. Integration of dt is t plus c. So the c is constant of integration. Now let us find the value of c. After integrating the differential rate law, we have arrived at the expression concentration of R is equal to minus Kt plus C. Let us denote this equation as 1. Here C is constant of integration. Now let us find the value of C considering the initial time t is equal to 0. So when time was 0, during the beginning of reaction, concentration of reaction was equal to the initial concentration of the reaction R naught. Let us substitute this in equation 1. So now at time t is equal to 0, concentration of R is R naught, which is equal to minus K, time is 0 plus C. So therefore we can write C is equal to R naught. Let me denote this as equation 2. Now I'll substitute equation 2 in 1. That is, I am substituting value of constant of integration into equation 1. So I can write concentration of R is equal to minus Kt plus C is R naught. Rearranging this expression, I can write Kt is equal to R naught minus R, and therefore rate constant K is equal to R naught minus R divided by T. So this is the expression for rate constant of a zero order reaction, and the integrated rate law for zero order reaction is R is equal to minus Kt plus R naught. Either any of the formats you can write it. This gives the integrated rate law for a zero order reaction. If I consider the equation concentration of R is equal to minus Kt plus concentration R naught. Let me write this as equation 3. If I consider equation 3, that is concentration of R is equal to minus Kt plus initial concentration of reactant. This is of the form y is equal to mx plus c, which is a straight line. So when I plot a graph of concentration of reactant R versus time, I will get a straight line graph. So this is the graph that you will get when you plot concentration of reactant versus time. So here we see that the intercept is the initial concentration of the reactant R naught, and slope of the graph will give us rate constant. Okay, so rate constant is equal to minus slope. So by calculating the slope, we can find the rate constant for a zero order reaction. Example for zero order reaction is decomposition of gaseous ammonia on the hot platinum surface at high pressure. This is the corresponding chemical reaction. It decomposes to give hydrogen and nitrogen gas. For this reaction, rate law is written as rate is equal to K into concentration of NH3 rise to 0, and therefore we can write rate is equal to rate constant. Now let us derive the integrated rate law for a first order reaction. So let us consider a first order reaction are giving products. We know that rate of a first order reaction is directly proportional to the first power of concentration of reactants. So therefore I can write rate law, rate is equal to K into concentration of R raised to 1. So the differential rate law is minus dr divided by dt is equal to K into concentration of R. Rearranging this equation, we can write dr divided by concentration of R is equal to minus K into dt. Integrating this expression on both sides, I can write integration of dr divided by concentration of R, which is equal to minus K is a constant, integration of dt. So we know that integration of 1 by x into dx is ln x. So here integration of 1 by r into dr is ln r, which is equal to minus k. Integration of dt is t. So it is k into t plus integration constant c. So right, c is constant of integration. I'll denote this equation which is obtained after integration as equation 1. Now let's find the value of integration constant and substitute it. And time is 0. We have concentration of reactant R is equal to R naught. So that is the initial concentration of the reactant. So let me denote this equation which is obtained after integration as 1. In that expression, when time t is 0, concentration of reactant is R naught. So ln R naught is equal to minus K time t is 0 plus C. So therefore, we get constant of integration C is equal to ln R naught. Now let's substitute C in equation 1, and therefore I can write ln R is equal to minus Kt plus ln concentration of R naught. I'll write this equation as 2. Now if we observe this equation 2, this is of the form y is equal to mx plus c, which is the expression for a straight line. Now let us plot the graph of ln concentration R versus time t. We will be getting a straight line. In this graph, intercept will give us ln R naught and the value of slope will give us rate constant K. So from this slope, negative of this slope will give us rate constant. If I rearrange this equation 2, I can calculate the value of rate constant. So we shall rearrange it. I can write Kt is equal to minus ln R plus ln concentration or not. So this is ln R naught minus ln R, which is equal to KT. From the laws of logarithms, if we have ln m minus ln n, we can write it as ln m by n. Similarly, here I can write this is ln R naught divided by R, which is equal to KT. And therefore, I can write K is equal to 1 by T ln R naught divided by R. If I need to write this natural log in terms of logarithm to the base 10, I have to multiply it with 2.303. So the value of K is equal to 2.303 divided by T log of R naught divided by R. So it's using either of these two expressions, you can find out the value of rate constant mathematically. So from equation 2, at time t1, I can write ln concentration R1 is equal to minus K T1 plus ln concentration R0. And similarly at time T2, I can write ln concentration R2, because at a time 2 concentration of reactant will be R2, that's equal to minus K T2 plus ln R0. Let me denote these two equations as equation 3 and equation 4. Subtracting equation 4 from equation 3, I can write ln R1 minus ln R2 is equal to minus KT1 plus ln R0 minus of equation 4, it's minus KT2 plus ln R0 is equal to minus KT1 plus ln R0 minus of minus plus KT2 minus ln R0. So ln R0 terms gets cancelled with one another. On the left hand side, we have ln R1 minus ln R2. Using laws of logarithms, I can write this as ln R1 divided by R2. So now this is equal to K T2 minus K T1. So rate constant is same. So it's K is common. K into T2 minus T1, which is equal to ln R1 divided by R2. And from this I can write K is equal to 1 by T2 minus T1 ln R1 divided by R2. So using this expression, we can determine rate constant for a given reaction at two different time T1 and T2, and the corresponding concentration is R1 and R2. So if we want to determine rate constant in terms of logarithm to the base 10, I have to multiply here with 2.303 divided by T2 minus T1 log of R1 divided by R2. So making use of any one of these expression, we can determine rate constant at 2 time T1 and T2 when corresponding concentration of reactants is provided to us. Again, considering equation 2, we can write this as ln R0 divided by R, which is equal to minus KT. Taking antilog on both sides of this equation, you can write this as R0 divided by R is equal to e to the power minus kT. And therefore, we can calculate initial concentration of the reactant R0, that is equal to concentration of the reactant at the time interval t, that's R, into e to the power minus kT. So this is how we can determine the initial concentration of the reactant involved in a reaction. We had written the expression for rate constant as K is equal to 2.303 divided by T log R0 divided by R. This can be rearranged and we can write it as log R0 divided by R, that's equal to K into T divided by 2.303. So here now if we plot a graph of log R0 divided by R versus time, we will get a straight line graph. Slope for this graph is equal to K divided by 2.303. So this, using this slope value, we can calculate rate constant. So that is equal to 2.303 into slope. Hydrogenation of ethene is an example for first order reaction. Chemical equation is C2H4 gas plus H2 gas. So we all know that hydrogenation is addition of hydrogen. So that alkene is getting converted into alkane. So ethane is the product that we are going to get. So if we write the rate equation, we observe that rate is equal to K into concentration of C2H4. Another example is decomposition of N2O5. Also the decomposition of N2O are first order reaction, and you should remember that the natural and artificial radioactive decay of unstable nuclei are always a first order reaction. So this is important to remember. Natural and artificial radioactive decay are first order reaction. For example, radioactive decay of 88 radium 226 to form helium and radon is a first order reaction. So the experimental rate equation here is observed to be rate is equal to rate constant into concentration of radium. Let us discuss how we can write integrated rate equation for a first order gaseous reaction. So for this purpose, let us consider a first order gaseous reaction. Where from gaseous reactant A, we will be getting gaseous products B and C. Now let us consider initial pressure of A as P1. So let P1 be initial pressure of A we are considering pressure here because for the gaseous reactants or products, its concentration is represented in terms of its partial pressure. So here P1 is the initial pressure of A, and let us consider PT as the total pressure. At time T. is total pressure Pt at any time. If we consider, that will be the sum of pressures of reactant A and products B and C. So units will be in terms of units of pressure. Here PA, PB, PC are the partial pressures of A, B and C respectively. If I consider the reaction A giving products B and C, initially when time t is 0, we have the pressure of reactant, that's the initial pressure, P1 atmosphere. So no products will be formed initially, so their pressure is 0 atmosphere. Now at a time t, let us consider the decrease in pressure of reactant B, X atmosphere. So the pressure at the time interval t will be P minus X, because X atmosphere decrease is observed in the pressure of the reactant, because reactants are getting converted into product, and therefore pressure of products will be X atmosphere each. Now at time t, total pressure is Pt, so which is sum of the pressures of A, B and C. So that is P1 X plus X plus X, which is the pressures of A, B and C. So here minus X and plus X gets cancelled with one another. So I can write Pt is equal to P1 plus X. So rearranging this expression, I can write the decrease in the pressure of the reactant X is equal to Pt minus P1. Let me write this equation as 1 and the equation for X as 2. We know partial pressure of A, that we have represented as PA at time t is equal to P1 minus X. So here I will substitute X is Pt minus P1, which is equal to 2P1 minus Pt. So we know that rate constant K for a gaseous reaction is written as 2.303 divided by T log of P0 by P, where P0 is the initial pressure of the reactant and P is the pressure of reactant at time interval T. So now we have considered that the initial pressure of the reactant A as P1 and the pressure at a time interval T is considered as PA. So our formula will become K is equal to 2.303 divided by T log P1 divided by PA. Substituting into this particular equation, K is equal to 2.303 divided by T log initial pressure, that's P1, divided by partial pressure of the reactant A at time interval T is 2P1 minus Pt. So this is the expression for rate constant of a first order gaseous reaction. Let us solve a few numericals based on the rate and rate constant of first order reaction. So the question is, for a first order reaction A giving products P, the concentration of A decreases from 0.5 molar to 0.4 molar in 10 minutes. Calculate the rate constant of the reaction. Again, let us read the question and let us list the data that is given. So they told that for the first order reaction A giving product P, concentration of A is decreasing from 0.5 molar to 0.4 molar. So means the concentration is getting reduced. Initially it was 0.5 molar, later it was 0.4 molar. So this 0.5 molar is the initial concentration of A. So I'll write this as A naught. And 0.4 molar is the concentration of the reactant after 10 minutes. So I'll write this as AT. And the time they have given us, it is 10 minutes. So in the 10 minutes interval, the concentration of reactant is changing from 0.5 molar to 0.4 molar. And we are asked to calculate rate constant, that's K, for this particular reaction. So we know that for a first order reaction, rate constant K is given by 2.303 divided by T into log initial concentration of reactant divided by concentration of reactant at that particular time. Okay, R naught divided by RT. Since our reactant is A here, the same formula can be written as 2.303 divided by T log A naught divided by AT. So let us substitute into this formula and let us find the value of rate constant. So we have 2.303 divided by T, that is 10 minutes, log of initial concentration, it is 0.5 molar, divided by concentration at time T, that's 0.4 molar. This molar and molar gets cancelled. We need to calculate log 0.5 divided by 0.4. 2.303 divided by 10, that will become 0.2303, and log of 0.5 divided by 0.4 is 1.25. This is equal to 0.2303 into log of 1.25, that comes out to be 0.0969. After multiplying this, we get rate constant for the given reaction is equal to 0.0223, and the unit is that of the time, so it's minute inverse. It's because here in the denominator we have 10 minutes. Taking that into numerator, that would become minute inverse, and therefore the rate constant of this particular reaction is 0.0223 minute inverse. Next question. 75% of the first order reaction is completed in 30 minutes. Calculate the rate constant of the reaction. In the question, they have given us 75% of the reaction is completed in 30 minutes. So let us consider the initial concentration of the reactant R naught is 100. So since they are telling that in 30 minutes 75% of the reaction is completed, let the initial concentration of the reactant be 100. Now the concentration at the time T, that is 30 minutes. So 75% of the reaction is completed. So the concentration is 100 minus 75, that is equal to 25. So the time here is 30 minutes, and therefore T is equal to 30 minutes. So we need to calculate rate constant. We have the expression for rate constant of first order reaction. K is equal to 2.303 divided by T log initial concentration of the reactant R naught divided by concentration of reactant at a time T. Substituting into this, 2.303 divided by time, that is 30 minutes, log of concentration of the reactant initially 100 divided by concentration of the reactant that is left at time interval T, we have it as 25. Simplifying this, 2.303 divided by 30 into log 100 by 25 is 4. Evaluating the value of log 4. Writing other terms as such. 2.303 divided by 30 into log 4, which is 0.6020. Further, upon simplification, we find the value of rate constant as 0.0462 in the unit of minute inverse. So it's because time is in denominator. When it goes to numerator, the unit will become per minute. And therefore, rate constant of the reaction is 0.0462 minute inverse. Consider a reaction R giving products P. If the initial concentration of the reactant is R0, the time required for the concentration to become half of it, that is R0 divided by 2, is the half-life of the reaction. So, half-life of a chemical reaction is the time in which concentration of a reactant is reduced to half of its initial concentration. The half-life for a chemical reaction is represented as T-half. Half-life of a reaction is the time in which initial concentration of the reactant is reduced to half of its initial value. At T is equal to 0, say suppose if we have concentration of the reactant as R0, then T half is the half-life of the reaction, where this concentration will be R0 divided by 2. That's half of the initial concentration. Now, let us find out what is the half-life for a zero-order reaction. For a zero-order reaction, its rate constant is given by K is equal to initial concentration minus concentration at a time T divided by T. When T is equal to T half, we have the concentration of reactant at that time interval is half of its initial concentration. So substituting this into the expression of rate constant, we can write rate constant at T half is K is equal to R0 minus R0 divided by 2 divided by T half. Rearranging this, I can write T half is equal to R0 divided by 2K. So this is the expression for half-life of a zero-order reaction. So from this equation, clearly we can tell that half-life of a zero-order reaction is directly proportional to the initial concentration of the reactant, and half-life of a zero-order reaction is inversely proportional to the rate constant of the reaction K. In a similar way, how we have arrived at the T half for zero-order reaction, now let us write it for first-order reaction. We know that for a first-order reaction, rate constant K is equal to 2.303 divided by T log R0 divided by R. So now when T is equal to T half, we have concentration of the reactant R is equal to R0 divided by 2. So therefore, rate constant K is equal to 2.303 divided by T half, which is equal to log R0 divided by R0 by 2. So here R0 and R0 gets cancelled, so which is equal to 2.303 divided by T half into log 2, and therefore K is equal to 2.303 divided by T half, log 2 is 0.3010, K is equal to 0.693 divided by T half. So this is the rate constant for half-life of a first order reaction. Rearranging this expression, I can write half-life for a first order reaction is 0.693 divided by rate constant K. From this expression, we can tell that half-life of a first order reaction is inversely proportional to the rate constant, and clearly we can see that half-life of a first order reaction is independent of the initial concentration of the reactant. T half is independent of initial concentration of the reactant R naught. Let us consider an example to see how we can calculate the half-life period for a first order reaction. So the question is, the rate constant of a first order reaction is 200 per second. What is the half-life period? In the question, the rate constant for a first order reaction is given. So we have K is equal to 200 per second. What is the half-life period? So we need to calculate T half for this first order reaction. We know that half-life of a first order reaction is given by T half is equal to 0.693 divided by rate constant K. Substituting the value of K, I can write T half is equal to 0.693 divided by 200 per second. Simplifying, 0.693 divided by 200, that comes out to be 0.0034. And the second inverse, which is in the denominator, once we bring it to numerator, that would become second. So therefore, T half for the given reaction is 0.0034 second. So this is how you can find out the half-life period of a first order reaction by knowing the rate constant of the first order reaction. Let us consider a numerical related to the radioactive decay of a sample. The question is, half-life for decay of radioactive carbon-14 is 5730 years. An archaeological artifact containing wood has only 80% of the carbon-14 activity as found in living trees. Calculate the age of the artifact. So we know that all the radioactive decay is first order reaction. Here they have given us the half-life, that is T half for the radioactive decay, that is 5730 years. So they have found that the sample had 80% of the carbon-14 activity when it is found with respect to that of the living trees. So considering this, we can write that the concentration of the sample at the time interval is 80% of that of the initial value. So it's 80% of the R naught. So 80% means it's 80 by 100 of R naught, and therefore that is equal to 0.8 times of the initial concentration of the sample. So using this value, that is the T half, we can find the rate constant for this particular radioactive decay. So using this rate constant value, we can find the age of the sample as required in the question. So the main base for this thing is that you should always remember that all the radioactive decay is first order reaction. So this is what is important to remember. So since T half is given, we can calculate K, that is 0.693 divided by T half. So that's equal to 0.693 divided by T half is 5730 years. I'll write it as Y. So simplifying, 0.693 divided by 5730, that is equal to 1.21 into 10 to the power minus 4 per years. So this is the value of rate constant. Now we know For a first order reaction, rate constant is given by K is equal to 2.303 divided by T into log R0 divided by R. That is the initial concentration of the sample divided by the concentration at a particular time interval. Now here we need to find the age of the artifact, nothing but we have to find the value of T. Substituting the value of K, 1.21 into 10 to the power minus 4 per years, which is equal to 2.303 divided by T into log R0. The value of R is 0.8 times of R0. Further simplifying, I can write T is equal to 2.303 divided by 1.21 into 10 to the power minus 4 per years, log of 1 divided by 0.8, that's 1.25, which is equal to 2.303 divided by 1.21 into 10 to the power minus 4 per years, log of 1.25 is 0.0969. Further simplifying all these values, we get T is equal to 1844 and the unit is years. So therefore we have found out the age of artifact, and that's equal to 1844 years. So this is how you can solve this particular problem. Let us summarize the mathematical features of integrated rate laws of zero order and first order reactions. The order of reaction can sometimes be altered by certain conditions. There are many reactions which obey a first order rate law, although they are higher order reactions. For example, consider the hydrolysis of ethyl acetate, which is a chemical reaction between ethyl acetate and water. In reality, this reaction is a second order reaction, and concentration of both ethyl acetate and water affect rate of this particular reaction. So the rate law is rate is equal to K into concentration of ethyl acetate raised to 1, concentration of water raised to 1. But if we take water in large excess for the hydrolysis, the concentration of water is not altered as much as during the reaction. Thus, the rate of reaction is affected by concentration of ethyl acetate only. Therefore, rate expression is rate is equal to K into concentration of ethyl acetate raised to 1, concentration of water raised to 0. So, the reaction behaves as first order reaction. Such reactions are called as pseudo first order reactions. Inversion of cane sugar is another example for pseudo first order reaction. Here, rate law is rate is equal to K into concentration of C12H22O11. It has been found that for a chemical reaction with rise in temperature by 10 degree, the rate constant is nearly doubled. It means that if we rise temperature by 10 degree, rate constant will become double. The temperature dependence of rate of chemical reaction can be accurately explained by Arrhenius equation. It was first proposed by J.H. Wadhoff, but Arrhenius provided its physical justification and interpretation. So the Arrhenius equation is mathematically represented as K is equal to A into e to the power minus EA divided by RT. In this expression, K is rate constant, A is Arrhenius factor or frequency factor. It is also called as pre-exponential factor. This pre-exponential factor is a constant specific to a particular reaction, and R is gas constant, EA is activation energy, which is measured in the units of joules per mole. Let us consider a simple reaction and try to understand. Consider the reaction between hydrogen and iodine to form hydrogen iodide. So the chemical reaction is H2 gas plus I2 gas giving 2Hi gas. Now, according to Arrhenius, this reaction can take place only when a molecule of hydrogen and a molecule of iodide collide to form unstable intermediate as shown in the figure. This intermediate exists only for a very short time and then it breaks up to form two molecules of hydrogen iodide. This intermediate is called as activated complex. The energy that is required for the formation of activated complex is known as activation energy, and the activation energy is represented by EA. A graph that is obtained by plotting potential energy versus reaction coordinate is shown here for your reference. The reaction coordinate represents the profile of energy change when reactants change into products. The fraction of molecules which have energy either greater or equal to activation energy is given by e to the power minus EA by RT. If X is that fraction of molecules which have energy greater or equal to activation energy, then the mathematical representation is X is equal to NE divided by N, which is equal to e to the power minus EA divided by RT. Let us see how we can calculate activation energy by using Arrhenius equation. Arrhenius equation is K is equal to A into e to the power minus EA divided by RT. Write this as equation 1. K is rate constant, A is Arrhenius constant or pre-exponential factor, EA is activation energy, R is gas constant, T is temperature. Here we will take natural log on both sides of the equation. I can write ln K is equal to ln A minus EA divided by RT. Let me write this as equation 2. Now, this equation is of the form y is equal to mx plus c, which is a straight line. When we plot a graph of ln K versus 1 by T, we will get a straight line. Here m, that is the slope, that will be equal to minus EA by R, and the intercept C is ln A. For this graph, intercept is ln A and slope is minus EA divided by R. So from the slope, we can calculate energy of activation, and from intercept, we can calculate the value of A. So from this Arrhenius equation, we can tell that increase in temperature or decrease in activation energy will result in increase in the rate of the reaction. And there will be an exponential increase in the rate constant. At temperature T1, I can write this equation 2 as ln K1. K1 is rate constant at temperature T1, which is equal to ln A minus EA divided by R T1. And at temperature T2, ln K2 is equal to ln A minus EA divided by R T2. Let me write these equations as 3 and 4. So here K1 and K2 are rate constants at temperature T1 and T2 respectively. Now if I subtract equation 3 from equation 4, I can write ln K2 minus ln K1 is equal to ln A minus EA divided by RT2 minus of ln A minus EA divided by RT1. This is equal to ln A minus EA divided by RT2 minus ln A plus EA divided by RT1. So ln A and ln A gets cancelled. We have ln K2 is minus ln K1 is equal to minus EA divided by RT2 plus EA divided by RT. On the right hand side, I can take out EA divided by R as a common term. We are left with 1 by T1 minus 1 by T2. And on the left hand side, I can write this using laws of exponents as ln K2 divided by K1. So this is equal to EA divided by R into 1 by T1 minus 1 by T2. Or I can write this as ln K2 divided by K1 is equal to EA divided by R, and taking LCM, here we have T1 into T2 and numerator will become T2 minus T1. So this is the other way of how we can represent the same expression. Converting this natural logarithm to the base 10, I can write log K2 divided by K1, which is equal to EA divided by 2.303 R into T2 minus T1 divided by T1 into T2. It's if we rearrange this expression, I can write EA is equal to 2.303 R T1 into T2 divided by T2 minus T1 into log of K2 divided by K1. So it's using this expression you can calculate activation energy for a reaction when you know rate constants at two different temperatures. Now let us try to understand the effect of catalyst on a chemical reaction. To understand the effect of catalyst, we should know what a catalyst is. A catalyst is a substance which increases the rate of reaction without itself undergoing any permanent chemical change. For example, consider a situation. Your parents had made up their mind to buy a brand new mobile phone for you after you complete your PU exams. You are already preparing well for your exams. Your parents come to you and tell you that if you top your exams, they will present you a new mobile phone, or else they will not present a phone for you. What will be the effect of this offer on you? You will put in extra efforts to top the exams, right? If you were waking up at 6 a.m. to prepare for your exams, now you would wake up at 4 a.m. to study for your exams. Your preparation will go to next level. Am I right? This is what a catalyst does in a chemical reaction. It speeds up the reaction. If you top the exams or not, you will get the mobile phone for sure, as your parents already decided to buy a new phone for you. During the reaction, catalyst is not undergoing any change. Now, what if the added substance reduces the rate of reaction? Then it is not a catalyst, it is called an inhibitor. Now the question is, how does this catalyst increase the reaction rate? The catalyst provides an alternate pathway for reaction mechanism by reducing the activation energy between the reactants and products, hence lowering the potential energy barrier as shown in this particular figure. From Arrhenius equation, we can tell that lower the value of activation energy, faster will be rate of the reaction. Here you should note that a catalyst does not alter Gibbs energy delta G for a reaction. It catalyzes the spontaneous reaction but does not catalyze non-spontaneous reaction. It is also found that a catalyst does not change the equilibrium constant of a reaction, but it helps in attaining the equilibrium faster, as it catalyzes forward reaction as well as backward reaction to the same extent. The equilibrium will be attained faster. Collision theory, which was developed by Max Strauss and William Lewis, provides a greater insight into various aspects of a chemical reaction. Collision theory is based on the kinetic theory of gases. According to this collision theory, the reactant molecules are considered as hard spheres, and reaction occur between them when these molecules collide with one another. The number of collisions per second per unit volume of the reaction mixture is known as collision frequency, and this collision frequency is represented by Z. Another factor which affects rate of chemical reaction is activation energy. For a bimolecular elementary reaction A plus B giving products, rate of reaction can be expressed as rate is equal to ZAB e to the power minus EA divided by RT, where ZAB represents the collision frequency of the reactants A and B. E to the power minus EA by RT represents the fraction of molecules with energies equal to or greater than activation energy. Comparing this mathematical expression of collision theory with the equation of Arrhenius equation, we can say that A is related to collision frequency ZAB. The expression rate is equal to ZAB e to the power minus EA by RT predicts the value of rate constant fairly accurately for the reactions that involve atomic species or simple molecules. But for complex molecules, significant deviations are observed. The reason is that all the collisions do not lead to formation of products. For example, consider the collision between two trucks. If they just come and touch one another, no damage will take place. So I can consider this collision as ineffective. If any damage has to take place, two trucks should come with high speed and they must collide with one another. The second point that you need to consider is that two trucks, if they are just moving past one another, now this collision will also not result into any damage. So here I speak in terms of orientation. So how the two trucks are oriented with one another. For a chemical reaction, the collisions in which molecules collide with sufficient kinetic energy. So this sufficient kinetic energy, we call it as threshold energy, and the molecules which has proper orientations. They facilitate breaking of bonds between reactant species and formation of new bonds to form products. So such collisions are called as effective collisions. To account for this effective collisions with respect to a chemical reaction, another factor which is called steric factor or probability factor represented by P is introduced in the mathematical expression. It takes into account of the fact that in a collision, molecules must be properly oriented. So the mathematical expression is rate is equal to P into ZAB into e to the power minus EA divided by RT. Thus, in collision theory, activation energy and proper orientation of the molecules together determine the criteria for effective collision and hence rate of chemical reaction. For example, formation of methanol from bromoethane. This depends upon the orientation of the reactant molecules as shown in this figure. If OH minus is approaching from a side of Br minus, no product is formed. The product will be formed when OH minus is approaching bromoethane from the side that's opposite to Br minus. The proper orientation of reactant molecules lead to bond formation, whereas improper orientation makes them simply bounce back and no products are formed. Let us try to solve a few numericals based on Arrhenius equation and activation energy. So the first question is, the rate constant of a reaction is 1.5 into 10 to the power 7 per second at 50 degrees centigrade and 4.5 into 10 to the power 7 per second at 100 degrees centigrade. Calculate the value of activation energy of the reaction. So here we are asked to calculate activation energy of the reaction. Let us see and list what are the other data that is provided to us in this particular question. So they told that rate constant of the reaction is 1.5 into 10 to the power 7 per second at 50 degrees centigrade. We have given two different temperatures. So I write T1 is equal to 50 degrees centigrade and corresponding rate constant I write this as K1. So T1 is 50 degrees centigrade and the rate constant is 4.5 into 10 to the power 7 per second at 100 degrees centigrade. So another temperature has been given. I'll denote this as T2, that's equal to 100 degrees centigrade. Corresponding rate constant, I'll denote this as K2. Now the temperatures are in terms of degree centigrade, which has to be converted into Kelvin. So we will add plus 273. So it's 50 plus 273 Kelvin. That's equal to 323 Kelvin. Similarly, 100 degrees centigrade. So it's 100 plus 273. That's equal to 373 Kelvin. So we are calculate the activation energy of the reaction. So here we have the formula log K2 divided by K1 is equal to EA divided by 2.303 into R T2 minus T1 divided by T1 into T2. So this equation has been derived from Arrhenius equation, that's using the expression for rate constant at two different temperatures. I can rearrange this equation and I can write EA is equal to 2.303 into R divided by T2 minus T1 into T1 into T2 log K2 divided by K1. So here the value of R is equal to 8.314 joule per mole per Kelvin. So rest of the things already we have listed, K1, K2, T1, T2. Now let us substitute all these values into the expression for activation energy. So we have EA is equal to 2.303 into 8.314 into T1 into T2. So T1 is 323 Kelvin into T2, that is 373 Kelvin divided by T2 minus T1, that is 373 minus 323 multiplied by log K2 divided by K1. K2 is 4.5 into 10 to the power 7 per second divided by K1 is 1.5 into 10 to the power 7. Let us simplify this. So you can write activation energy EA is equal to 2.303 into 8.314 into 323 into 373 divided by 373 minus 323, that's 50, into log of 4.5 divided by 1.5, that's equal to 3. So after finding log 3, and that value is equal to 0.4771, multiplying all these terms and dividing by 50, we find activation energy is 22,011.75. The unit is joules per mole. Converting this into kilojoules per mole, I can write 22.011 kilojoules per mole. So this is the activation energy, that is what we are asked to calculate, which is equal to 22.011 kilojoules per mole. Second question, the activation energy of a reaction is 94.14 kilojoules per mole and the value of rate constant at 313 Kelvin is 1.8 into 10 to the power minus 5 per second. Calculate the frequency factor A. So here in the question, they have given us the activation energy for the reaction, that is equal to 94.14 kilojoules per mole, whereas the SI unit of activation energy is joules per mole. So converting this into joules per mole, I can write 94.14 into 10 to the power 3 joules per mole. And also they have given us the value of rate constant, K is equal to 1.8 into 10 to the power minus 5 per second. And this is the value that they have found out at the temperature 313 Kelvin. And we are asked to find the frequency factor A. So from the Arrhenius equation, we have K is equal to A into e to the power minus EA divided by RT. So here we need to find the frequency factor A. So by taking log on both sides, I can write log K is equal to log A minus EA divided by 2.303 into RT. Rearranging this expression, I can write log A is equal to log K plus EA divided by 2.303 RT. So now let us substitute all the data into this particular equation and we will find log of Arrhenius frequency factor A. Then we will take antilog to find the value of Arrhenius frequency factor A. So for this equation, the value of R is 8.314 joules per mole per Kelvin. Other values we have already listed from the question. Substituting, I can write log A is equal to log of rate constant, that's 1.8 into 10 to the power minus 5, plus EA, that's activation energy, 94.14 into 10 to the power 3, because the SI unit is joules per mole, divided by 2.303 into R, that's 8.314, into temperature in Kelvin, that is 313. Let us simplify this. Log, this is of the form log m into n, which can be written as log m plus log n. So I can write this is equal to log 1.8 plus log 10 to the power minus 5 plus 94.14 into 10 to the power 3 divided by 2.303 into 8.314 into 313. Log 1.8 is 0.2553 plus, we know log m to the power minus n can be written as minus n into log m. So here we have minus 5 into log 10 and the value of log 10 is 1, plus simplifying this term we get it as 15.7082. So this is equal to 0.2553 minus 5 into 1 is minus 5 plus 15.7082. Further simplifying, we get the answer as 10.9635. But this value is log A. In order to find the value of Arrhenius frequency factor A, now we need to determine anti-log of 10.9635. So once you note the anti-log, you will get it as 9.194 into 10 to the power 10. And therefore, the value of A is 9.194 into 10 to the power 10. Third question. When a graph is plotted for log k versus 1 by t, a straight line with the slope minus 6670 is obtained. Calculate the energy of activation for this reaction. So in the question, they have told us that the plot of log k versus 1 by t was plotted and it was a straight line with negative slope. So the value of slope that's found out to be minus 6670. We are asked to calculate the energy of activation EA for this particular reaction. So we have the Arrhenius equation. K is equal to A e to the power minus EA divided by RT. Upon taking log, we can write this as log K, which is equal to log A minus EA divided by 2.303 RT. So from this equation, we can plot log K versus 1 by t. Whereas here in this particular equation, if we write this in the form of y is equal to mx plus c, here I can write this as c minus mx. We would obtain a negative slope. Okay. So here y is log k and x is 1 by t. So we have c, that is intercept here, is equal to log a. And the value of slope we have is that's equal to, other than 1 by t, rest of the term is m. So we have it is minus EA divided by 2.303 into R. Now if we plot the graph of log k versus 1 by t, this is how the graph looks like. The slope for this plot of log k versus 1 by t, that was found to be minus 6670. So this slope value here, that is minus 6670, that is equal to minus EA divided by 2.303 into R. Now let me rearrange this to calculate the activation energy. So minus and minus, that would become plus. So EA is equal to 2.303 into R into 6670. The value of R is 8.314 joule per Kelvin per mole. Substituting that into 6670. And this is equal to 127710.46. The unit is joules. Now let us write this answer for activation in terms of kilojoules per mole. So it is 127.71 kilojoules. And therefore, the required answer, that is the activation energy, is 127.71 kilojoules per mole. Because the activation energy is told in terms of kilojoules per mole. The answer is 127.71 kilojoules per mole. Thank you for watching. If you have any suggestions for us, you can post your suggestions in the comment section below this video. If you have not watched our other NCERT classes, you can watch them by clicking on the playlist below. I'll meet you in my next video. Take care. Bye-bye.